Hey guys, in this video I'm going to go over multi-level models. This is from a lecture that I did live in person last year, a couple years ago, and it has lots of noise and lots of things going on because there are real people in the room, so I'm re-recording that version with actually another example of an MLM so that I have a couple of MLMs on my YouTube channel as well as like a more clean lecture that you can watch. So we're going to talk about multi-level linear models. I took these notes from Andy Field's Discovering Statistics in R and a little bit from just life running these things. So the first question really is, can I get the slides to go on? There we go. What are multi-level models? So why do people use them, and why do I think they're the best thing since sliced bread? Or for me, sliced cheese. And then how do I analyze those models? So we're going to get into how MLM works, and the kind of point of MLM, and then how do I analyze that set of models. So let me hit this button so it's a little clearer. And so the whole point of these designs is to help you control for hierarchical data. And so data is often structured in a way that is nested is the word that people tend to use, and it's structured. So let's say we're talking about education research and we want to look at children in the classroom. Well, you can't randomly assign a classroom, and they're nested within. So they're structured within a classroom that has a specific teacher. And then for me in my research, a lot of times data points are nested within people. So two examples. One, we were looking at the supplemental instruction program here on campus. And for that particular problem, we were dealing with the fact that students were nested within course. So that course had a specific instructor and leader within a specific semester. So it had this kind of tiered hierarchy that we had to deal with because students within the next semester take a different course, but it was still within that same hierarchy. So they would be in the study multiple times. So anytime you have repeated data, this analysis really can help you. So I personally think if you know MLM, you don't need to know anything about repeated measures ANOVA or ANOVA or MANOVA, because you can handle the problems with the type of hierarchical data that repeated measures creates with a much more powerful statistical analysis. So anytime you have repeated data that you want to analyze using every single data point instead of creating averages for participants. So for a long time, this was not really a practical analysis because it really needs a computer to run. And so we would rely on taking very large data sets and reducing them down. So if your research involves using participants across multiple items or multiple time points, there's no need to reduce that data down to an average one score for them. Instead, use every single time point. So a study I've talked about a couple of times on my channel is some people who work on body image who test people 5 times a day, for 5 days. So they have 25 time points. Well, instead of making that one person one time point or one time point per day, now we can use all 25 time points. In my research, that's especially exciting because items like word pairs or just even the items that you show people on the screen can be tricky sometimes, and they don't always do what you expect them to do. And so this analysis allows me to keep every single item a participant saw. So that may be 100 to 300 data points instead of reducing them down to 1. And it also allows me, I can use this as a way to find bad items. So items that are very, very different from others. We won't really cover that today, but it's something I could do. So I'll give you an example of this idea of levels. So hierarchies have levels, and we want to test each level to see if it's necessary to control for that level. So here's an example of level 1 where I have each particular child in a study. In my studies, I'm going to talk about participants. So every participant is part of my study. And each of those is nested under a specific class. in our fake study here. And that might be a 3-level hierarchy where each child in this study is nested in a specific class, which is at a specific school. This is a very structured sort of levels. Now, for levels, that tends to be about how you're going to control for intercepts. So how, like sort of the random factor, the fact that, this child is in this class, which is in this school. In a study where we have lots of items, I can control for the randomness of participants, and then I can see if the items add an extra level of kind of random noise to the study. But for me, I have each participant has all 120 items or whatever, and so I want to control for the fact that every participant saw every item. And I'm going to use each data point and not average across participants and items. So here's an example that we're going to work on. So each person judges 120 items. I think in the study I have, it's actually 96 items, but either way, rather than creating an average judgment score, I can use those into item statistics. So I can take and use all 120 data points for each person, which means each person gives me 120 bang for my buck instead of 1 bang for my buck. So this is a repeated measures design that really allows me to use every single data point. And that's super important because that gives me a lot more power. Okay. Participant data might be collected on the same dependent variables over a span of several days. So that's another type of design that you might use. This is more of a longitudinal design. So MLMs can also be used to analyze growth data. It's very similar if you've taken my sim class or if you watched any of those videos to latent curve modeling. It's a more traditional regression instead of structured equation model. But if you've done both of those, you'll see the similarities between the steps in those procedures where we're looking at if there is change over time. So something funny from the Andy Field book, ordinary regression turns itself into cheese. So you guys know I love cheese and I love cheese examples. Cheese and hides itself in the fridge at the prospect of the fact that data cases are related. So regression just sort of melts when you have participants in there multiple times. Multi-level models eat this for breakfast. So it's regression flavored cheese. I just thought it was a very funny phrase because I love cheese. So thank you, Andy, for the cheese and wine examples in your book. So what are the benefits? Why do a multi-level model? Other than the power thing that I've already covered, which will be on another slide here in a minute. But actually, you can break homoscedasticity. So it's almost assumed that thing is actually not going to work. So I can actually model that variability in the regression slope. So remember, homoscedasticity is when we get that fan picture in a residuals plot, or heteroscedasticity. And often we attribute that to either a variable that we didn't take that has caused this fan effect in the slopes, or it's residual error that we can't figure out what the hell is going on usually. And in these types of models, I can actually model that. I don't know that it necessarily explains what's happening if you get random slopes significant, which you'll see in this example. Hold on, there's a big old cat in the way. There we go. Where are we at? So I don't know that these models explain heteroscedasticity unless you've got the variable there, but you can test for it a little better and talk about it better than just kind of doing the shrug dance of like, well, it happened, I don't know why. The biggest thing is this assumption of independence. So this is an assumption you test for. Remember, independence is the assumption that every participant's data point is separate from every other participant's data point. And that's not always true. And in these particular cases, if I'm going to use every single data point for participants, so like item 1, item 2, item 3, that is most certainly not independent. So we can deal with correlated error. So you'll hear me say this a lot, especially if you watch the sim videos. Correlated error is a problem. meaning that the error for item 1 is correlated to item 2, or the error for participant 1 is correlated to participant 2. So I can actually deal with that error, that problem. And then missing data. So these are most well known for coping with missing data. And I would say that they used to be called hierarchical linear models. Now most people call them multi-level models. I don't know that there's much of a difference, just different approaches to the same idea. I've seen them called both ways. Sometimes I've seen them called mixed model repeated measures. Pick your favorite one. But one of the first enticing benefits for people was the dealing with missing data. And I mean that in the way that, let's say we're testing people over time and participant 12 misses point number 4. And often in a repeated measures ANOVA, you would just have to toss that person because it didn't have a complete data set. In the MLM, it would just kind of linearly interpolate between 1, 2, 3, and 5. So the nice thing is that missing data in this is not as big of a deal. Now, it will automatically exclude all of your NAs when we get to running this here in a minute in R. What I'm saying is that if I have participants' data points for 60 items and they're missing 2, I don't even need to necessarily make that data up or mice that data or impute it. It's just going to kind of figure out that that person's missing those 2 and work around it. If you have very specific time kinds of data, it will interpolate around those data points. So it allows you to use all of the data points, and if they're missing one, kind of no big deal. And then to me, the biggest draw, other than handling correlated error, stupid washing machine is so loud, and dealing with missing data is power. So instead of only 50 participants with 1 data point each, I'm now analyzing 120 points times 50 participants. And that gives me much better sampling. And I know I've said this across multiple videos, but work with all the data that you have. So if there's no reason to average the scores, don't. Use every data point that you get because you're going to get a much better picture. The more sampling points that we have, the better our analysis will be just in general because we have more power, because the sampling distribution will have a better idea of what's going on. Now, if you're working with scales that have total scores, obviously do that. But this isn't a case where I'm working with lots of items. Don't average them. Use every data point that you have. So we're going to do a very simple example from our lab that we might try. We wouldn't normally do response latencies because they suck, but an example from data collected in our lab. And what happened was we had people judging how related word pairs were, and we looked at how fast they did that. So we looked at the relatedness factor from 0 to 10 and the response latency, which is basically from 0 seconds to a whole bunch of seconds. And the way that we would level that data, or it's structured, is first level is participant. So we have, each participant has all of these other items. So we might add items as a potential second level. And so you can actually kind of think of those as flipped because every single item is under every participant, or the reverse, every participant is under every single item. So what you'll see when we run this is that only one of those is going to be useful. But it's always helpful to test the different structured levels in your data. And then for our independent variable, we're going to use the judgment that they gave the items, and for the dependent variable, we're going to use their response latency to those items. So let's talk a little bit about how that's going to work. So there are 2 different types of coefficients. And if you're used to regular regression, you're only used to one of these. Okay, so there are fixed coefficients and random coefficients. Fixed coefficients are those intercept slope values that are the same across different contexts, different people, different items, whatever context you're interested in. And that's the way that basic regression, multiple regression, hierarchical, simultaneous, like just your regular linear regression works, and ANOVA. And that means that every person has the same intercept. So we're creating one equation for the entire group of people. And I think that's a little bit of a bad assumption, because anytime you're working in the social sciences, people are weird. We talk a lot about dealing with missing data and outliers and dealing with the fact that people are difficult participants, right? So random coefficients allow you to vary either the intercept or the slope, and we'll do both, across people. And so that allows us some flexibility interpreting the data. Now, the problem with random coefficients is that you have to interpret random coefficients. Okay? A fixed coefficient is nice. For every 1 unit increase in latency or in response, we got 200 milliseconds increase in latency. Random coefficients require you to think about the fact that everyone is varying a little bit. But when you talk about people, that's not too surprising, right? That there's going to be a little variability. So some participants might just naturally be faster at working on a computer than other participants. So there's some pros and cons to using them. Random coefficients might explain the data a little better, but then you have to interpret them. So let's look at just some examples of how this might work. This is from the Indy field, so it's about Viagra. But this dashed fit line here is a regular regression where I would interpret everyone in the exact same way. The fit lines, the 3 different colored fit lines, are allowing for a random intercept. So you notice how the slopes are parallel. That allows each group has the same slope here. We're forcing the slopes to be the same. But we're allowing them to start in different places. And that's a fairly nice fit to the data because it allows the low-dose placebo and high-dose groups to each have a different y-intercept, right? So a different intercept, which means that they're starting at different places for their libido in this example. For us, that might mean for each participant, their judgment scores start in different places. And that's something that we've found is that each participant has sort of like an average level of rating that they give things, sort of regardless of the actual numbers you're supposed to be giving. And so some participants just like to rate things high and some participants just like to rate things low. And so that allows us to control for the fact that they kind of all start in different places. I really like random intercepts in the sense that if you want to think about school and education, some students are A students, some students are C students. And so random intercepts allow you to capture that fact. Now, in a perfect world, it would be better if they weren't random because then everybody's got the same pattern of data. It's much easier to explain. But in the real world, random intercepts might be a little more appropriate or more natural to what's actually happening in the world. Now, a fixed intercept is where they're all crossing the y-axis at the same place, approximately here, but they have random slopes. And so this is not too common of a model to test, but I can test random slopes and a fixed intercept. That means they all started in the same place, and then due to whatever intervention you gave, they all went in different directions. Now this one would be more common, a random slope and random intercept. And so what that means is that each of the slopes is different and they all started in different places. That's a little bit harder to interpret because what that means is that for every participant, each intercept is different and each slope is slightly different. So that gets kind of tricky, but it is a potential pattern that we can test. So we're going to test those against each other and determine which one is the best fit. Likely, including random intercept and slope is going to be a better fit because it allows for more flexibility in the model. You can usually cover more of the error that way. But we'll see what happens in this data set. So how do I compare models? And what we're going to do is we'll treat this in a very hierarchical fashion. we're going to build the models from the ground up because we don't really get traditional F values when we run MLMs. And so we have to have a way to determine if these models are significant. So we're going to start with our fixed coefficients and a null model, meaning just the intercept, a fixed intercept. And then we're going to change one piece at a time. The traditional pattern for this is to do a fixed intercept model, a random intercept model, add the fixed effects, fixed coefficients for your regression, and then add random slopes is the pattern that I've traditionally seen. And what we'll do is on each one of those steps, we'll assess the change between models. So we can use a couple of different things. We can use AIC, which is a Kaki's information criterion, or BIC, which is a Bayesian criterion. In both of those, lower values are better fits. So lower values means less error. They might be negative, but lower values are better fits. So always more lower. But the more traditional thing to do is to compare log likelihoods. Log likelihoods are a type of chi-square, and so we could use a chi-square difference test. And so the way this works, now it'll do this for you automatically, but it helps to know how it works in case something breaks. So it'll take the model 1 log likelihood, subtract the model 2 log likelihood. So whatever order you put this in, it needs to make sure the subtraction is positive, because chi-square is positive, should be positive. And so it'll create this difference score, and then it'll compare that to a critical score. So that critical score is a degrees of freedom difference. So subtract model 1 minus model 2 df. So this is how many pieces you changed. And it'll pull a chi-square alpha for you. So it'll test if that chi-square difference using those degrees of freedom difference is significant. Now once we try this in R using the ANOVA function, I'll explain this a little more, but essentially what it does is it takes a difference score between models and tests if that difference is greater than 0 using chi-square. Now when you're doing assumptions, you should check for accuracy. You still check for missing data, but you really don't generally impute missing data because that's naturally part of the appeal to using an MLM. We can look for outliers. Independence is an assumption that we're going to control for. We still want to check for additivity. We could potentially need to center our variables, which means that if you're doing interactions, you would need to take the mean and subtract from it. So what happens is I have each person's score minus the mean so that there's centered, not z-scored, but centered, where 0 is the mean and the scores range up and down. And that just helps sometimes make these models fit because they're not what we call closed form solutions. And what that means is this is an iterative process. So we iterate trying to find the best fit for the model. Unlike regular regression, which is just a mathematical churn, and it has a solution, a closed form solution. MLMs, not so much. So sometimes they will just break on you because they can't quite find the right solution. Clearly it should be linear. This is a multi-level linear model. The data should hopefully be normal, but we are using all of the data points, so this gives us a little bit of leeway on that normality one because we have lots of sampling data to work with. It should be homogeneic as best as possible, and we should still look at homoscedasticity, but we'll also be able to test for random slopes as the reason for heteroscedasticity. So 2 packages we're going to use. We're going to use nlme. There's another package called LME4, as in the number 4. But I like nlme better. It tends to run a little better. It also gives you p-values. Reshape if your data needs to be restructured. So the data set we're going to use is already in long format because thank God for the computer program that puts it in long format for me. I used to hate that because I would have to average everything and restructure it, but now I'm like, woohoo! So in wide format, participants each have their own row and the data is variabled in columns. In long format, the rows are your participants being measured multiple times. So this data is already in long format, but if your data is in wide format, you should switch it to long format using the reshape function. And this is mostly a lecture for my class, but I think I have a quick how to use reshape. So the melt function in reshape, and that's lowercase melt here, not uppercase. Open parentheses, the data frame name, and then you do ID equals, and those are constant variables you don't want to change. So what's like gender or participant number, so be sure you have a participant number in there or this whole thing won't work. And we want, those will be things that'll be repeated across columns, or across rows. So they go from being in their own column to a row. They go from being a column to another column, but it's repeated across each participant's rows. Measured variables are your repeated measures that you want to combine into one column. Okay. The biggest pain is if you have multiple repeated measures variables. And in that case, I would tell you to melt half the data, like split the data into the repeated components. So like repeated group 1, repeated group 3. Melt each piece and then combine them together. Because double melting is a big pain. Okay. All right. So here's how we run that analysis. So I've got this open in R, and then we're going to talk about how to do a couple things, and we'll come back to these models. All right. So I'm going to import my data. So I have actually recently restructured the way I run RStudio because I saw a former student of mine doing this, and it's like, shout out, it's awesome. So if you open RStudio normally, the console is down here on the bottom, but I moved it to be over here on the right, and I really love it because now I can see, thank you, kitty cat. Now I can see the when I'm running on the left and it actually running on the right. If you like that structure, you can do that on a Mac under Tools, Global Options, Pane Layout, and then you just kind of change them around. And this is where I found out that you can actually turn things off and on. It was pretty beautiful. On Windows, it's under File and then Preferences and then Panes. So just kind of a warning that everything that's going to happen here is going to be up here on the right. So let's look at my data here. So I've got participant number. The participant numbers are really crazy because a very long story about how we use participant numbers more than once by accident. So we created participant numbers based on the date and time that people took things, and then Excel made it this number. Either way, it's a unique number for every participant. I have trial codes here where each participant saw 96 different words or word pairs. So you can see that I have every participant and every trial. Latency here is their response latency, how long it took them to respond to that pair, and the response, which ranges 0 to 10, I believe. So this is already in long format. Now, if the data are in wide format before we start, data screen the whole thing in wide format. And that is because it allows you to control, like Mahalanobis wise, for the fact that these are the same participants tested multiple times. So I'm going to do the data screening in both ways. I'm going to do it sort of before the analysis and then show you how you could do it after the analysis. But it would be better if this were in wide format, because then I am controlling for the fact that participants are repeated and that correlated error thing. You can do it either way, so I'm going to show you both ways. So if I were to do data screening and we're already in wide format, I could look at a summary of the data. So I have participant number over here, which is not very useful, trial code. So how many times each word was seen. And you'll notice here under trial code that I clearly at one point had some missing data because participants, every word should have been seen an equal number of times, but clearly that didn't happen. So this is how it's going to handle missing data. Is real 48 here has multiple missing data points, but that's not going to, I don't need to exclude people because they missed that item. Our response latency here from way too short, so they never should have seen it, to way too long. I don't know why they stared at it for so long. But we'll deal with that as outliers. And then our response, the actual thing that they hit on the keyboard from 0 to 10. All right, so I don't really have any missing data because it doesn't say NA anywhere. Because if our participant didn't get a trial, it just left that line off. I've set up my Mahalanobis to ignore the first two because those are participant numbers essentially. And let's see what it will give us here for outliers. So remember, Mahalanobis is the data set minus any categorical columns. Call means minus those categorical columns. And covariance minus those categorical columns. Our cutoff score here is going to be a chi-square where we're going to use 0.001 minus those two columns. So if I wanted to see that cutoff, so our degrees of freedom would be in call example minus 1 and 2. So this should give me 2 degrees of freedom. And our cutoff score is 13.82. Our summary here, I've got mostly data that's within the range, but at least 40 outliers, so I'm going to exclude those. Now you can use a subset function or this version of it. Both are fine. This will works fine as long as there aren't any outliers. Missing data. We're excluding outliers right now. So I just eliminated some of these really long response latencies. So if I did a summary of my no-out data set, you'll see that the response latencies have gotten much shorter time-wise. Now, in real response latency data, there's a different way to deal with this sort of outlier problem, but we're just going to keep going, pretending like we're not going to double delete. Let's look at the correlation between our two predictors here. And we actually do want them to be correlated because it's our IV and our DV, but just showing you how you'd run additivity or multicollinearity. And so it says that there's basically no correlation here, because remember, a blank spot means it's less than 3. And that's because it says that the correlation is negative 0.26. I'm going to set up a fake regression to run here. And I'm going to tell it to only use the 2 columns I'm actually going to be interested in. Okay, so I'm going to exclude column 1 and 2 because those are not actually predictors, they're just participant numbers. And this is the same setup that I always use when I'm doing data screening. So I've created my fitted values and my standardized residuals, okay, or studentized residuals. Let's look at linearity. Okay. And it's not pretty. It is not pretty at all. It's mostly okay between 2 and 2, but that is distinctly chair-like. And so we might consider using a non-parametric design, but non-parametric multi-level models, kind of a pain. So we're gonna pretend here and know that that will reduce power. Our histogram of the standardized residuals is a little skewed. Most of the data is between 2 and 2 and centered over 0, but we got a little bit of skew out here. Not too concerned because I have 4,000 data points. And then, as you will see here, our standardized residuals are very, very not pretty. So the data, even if I could, exclude these couple of points out here, is very heteroscedastic. It's kind of a hot mess. So what we'll do is we'll run the analysis and see if controlling for those correlated error or correlated participants helps us out. So this sort of data screening that I just did would be much better if the data were actually in wide format, because then I could control for that fact that some participants are naturally slower than others, a little better for outlier analyses. Additionally, I could have controlled for correlated error. So if your data's in long format already, I'll show you at the end how you can analyze at least assumptions in long format. Outliers, you still gotta kind of handle the way we just did it. Okay. All right. So what we're gonna do now that we're running the analysis is compare two different models. So we're gonna look at model 1, which is our baseline intercept only model. And by intercept only, I mean literally just the intercept, which is essentially like testing the average Y score, average dependent variable score. Then we're going to see if we allow that intercept to vary across levels or participants, is that better? So this is essentially testing the necessity of nesting the data. If model 2 is better than model 1, then you have to run an MLM, or you need to, using finger quotes here. If model 2 is not better than model 1, you can happily ANOVA dance. Minus the fact that if you have structured data, people want you to control for structured data even if it's not necessary. So there are a lot of times when I'm reporting analyses where controlling for participants with the random intercept didn't do jack. Didn't help at all. Everybody had approximately the same intercept. But because we were using all of our data points and it was quite clear that we had structured data, we just went with it anyway. So we just went ahead and used that random intercept model, even though it didn't do a whole lot for us. So let's do that. So here's our intercept only model, but because we're not stacking or nesting the data, the function is GLS, okay, generalized least squares, instead of LM. So we want to do dv tilde iv, data equals no out here. Method equals maximum likelihood, because this is an iterative process. Any action is NA omit. At this point, I don't have any missing data, but it doesn't hurt you. Okay. So let's run that. Let's look at a summary here, which I have. Regression functions is just a reminder, y tilde x, but x here is just the intercept, so we use 1 to represent the intercept, so give me only the intercept, which is effectively testing the y-average. Is the y-average different from 0? Data equals data set name. This should be lowercase d. And then any other important stuff, which in our case is this method and NA action. So what this does is it allows me to look at that intercept. So that intercept here, this score here, is the average y score. So this is the average response latency in our study, standard error here, and that is significantly different from 0. So people are taking about 4 seconds to answer, because this is in milliseconds, and that's different from 0, which is, who cares? I'm not terribly interested in that. But you'll notice here that if you're used to regular regression, that we don't have an F statistic. So I can't really tell you if this is an important model. I can tell you that my intercept is greater than 0, which I don't know that I care too much, but there's nothing at the moment to compare it against. And instead what we want to do is come over here and run a random intercept model. Okay. We are switching to the LME function, but otherwise this looks very similar. Latency equals tilde 1, or tilde 1, so we're predicting latency for the intercept. Data, method, and NA action are all the same, is here, and here's the new part, is right here. Random equals tilde 1 for the intercept here by participant number. Okay, so this will set a random intercept for participants. which effectively means that every participant can have a slightly different average score across all of these items, which we would expect, right? So let's run that. Look at that. So before, the average score was 43.52, which I think is a little different than the one I got over here. So not sure why, but slightly different numbers here. This time, the average score is 41.80. The standard error has actually increased, right? But what we've done is added this random effects piece here. And what that does is it controls for the fact that every participant is starting in a slightly different place. And here's the standard deviation of that intercept. So that is how much the intercept varies, or this 4100 varies by participants. So that means that most of the data, most of the participants are somewhere between 3 something to 2700 if I can subtract that, and 5400 if I add that. So it allows for that, or 4200 here, to vary by this much, meaning that every person has a slightly different intercept, and this is the sort of main range where people's scores are ranging. The overall intercept is still significantly different from 0. Is this necessary? So was it necessary to nest by participants? And so you'll see here it says the number of groups. Number of groups here means the number of participants. So it's lumped all of these items into 54 groups because I have 54 participants. So the way to test if that's necessary is this ANOVA function. The ANOVA function does not actually run an ANOVA. It will compare models. And I have that over here. It might be slightly different. Like my AIC and my BIC, lower is better. So model 2 here is much better. The degrees of freedom, so it's testing 1 versus 2. Okay. It subtracts the log likelihood ratios. So it subtracts these two numbers and tests if that's different from, tests if that's different from 0. Okay. There's 1 degree of freedom different here. So the cutoff score for 1 degree of freedom, chi-square for 0.05, is 3.84, something in that range. So it's definitely way bigger than that. So it takes this difference score, this ratio here, and the difference here, and compares that to chi-square. So it says if I have a chi-square with 1 degree of freedom, and it's 986, what's my p-value? And that means that, yeah, we got to control for participants. Now, what if I wanted to control for participants and the trial codes? So let's see if it's necessary to also control for items. And this would imply that some items are really wildly different than other items, okay, even after controlling for participants. So where I add that is here. Notice the word list here. So I have to make a list of random intercepts to control for. So this will all control for participants and items. And so that's the big key difference here is the word list around this random intercepts. Okay, so that took a hot second to run. Now what you'll see is the fixed effect, it hasn't really changed, right? So that might imply that I don't need to do a whole lot. But it does show me that there's a lot more variance here. So the range around this is a lot bigger if I am controlling for items nested within participants. So for every participant and every item. Okay. And so down here it tells me how many participants are nested and then the number of trial codes. Okay. Now, is that necessary? So I'm going to run that ANOVA function again. And I included that here. And it's not significantly different. So it really wasn't necessary to do that. We're going to stick with only the participant level. And here that makes sense because every participant has every item. It's not really structured per se past the participant level. It might be necessary if we randomly picked and each participant only had 50 items and it was a random set of 50 items, then items might be more useful. But since every participant saw every item, participant and item is essentially the same, not quite the same variable, but a similar variable. So let's add fixed effects to the model now. We've decided to nest by participant and do random intercepts because that was better than not. And we're going to change out that 1 in our code for the variable name that we're interested in. So that's here in a predictor model. So now I have latency tilde response. The rest of it stayed the same. Now, all right, here's the good thing. So our intercept is going to change because now we have a predictor in the model. And so that's going to move the intercept around. But we would hope that the variance around that might decrease some, a little bit less error. And it's about the same. But our response is really what we're interested in. So for the response here, which is how related they think the word pairs are, for the more related words, meaning for every increase in response, meaning they think they're more related, we get a reduction in response latency. So the more related they are together, the faster they judge them. Okay? And that is significant. Right? So our t-value here is p less than 0.05. It also tells me how correlated the response is with the intercept, which implies that since we have random intercepts here, that where they're starting is a little bit tied to the slope. So this will be more important here in a minute. But I only have one predictor here, so I can probably tell you that this model is significantly different from the last model, but there's not really an F statistic for this model. So I could just report that the response was significant, end of story. But if you have multiple predictors here, you would really want to show that this model overall is better than an intercept-only model. And this is very similar to hierarchical regression. So let's say we had 3 predictors. We want to show that all 3 of them are significantly better than nothing. And then we might want to talk about each predictor individually. So that's why we're also going to add this ANOVA function. We're going to compare model 2 to model 3. Okay. So this compares 1 to 2 and then 2 to 3. And so that's what this test column is. So it's comparing each successive model. I don't really want to compare 3 to 1 because those are very different things. And that is significant. So when I only have one predictor, it's not really important. They tell me the same thing, but it's useful if we have multiple predictors to include that sort of thing. All right, last thing we're going to try here is random slopes. So random slopes is kind of like a moderation analysis without a real variable. This is where we can test maybe why we have heteroscedasticity. A random slope implies that every participant has a slightly different relationship from the IV to the DV. So that makes life a little tricky because if they all have slightly different relationships between the IV and the DV, what does that imply? Right? But we can look at how much that random slope varies. So we're going to change, and what this says right here is we're going to come down here and we're going to change here. So before we had a random, oops, sorry, I clicked in the wrong spot. Before we had this tilde1, and now we want to change it to the slope nested within the participant number. So we're changing it from a random intercept to a random intercept and a random slope. I have this control function in here because sometimes when you do both of these together, it will not run. So this nlme control allows you to increase the iterations in case it's slow to run. This particular one runs fine, but just as a FYI that sometimes this will not converge is the word, which means maybe try a couple more iterations. Let's look on model 4 here. All right. So what you'll see in a second is this model is significant. The relationship between the IV and the DV has actually gotten a little stronger. So these are like the overall statistics. But now I can look at the standard deviation around this response. So what does that mean? Well, I have a relationship that we talked about a minute ago where as the participant judgment goes up, their response latency goes down, which means that the more related they think it is, the more quickly they judge it. But that varies a lot. So the standard deviation for that is quite large, which implies that participants vary a lot around the sort of average score. So people are ranging from almost zero, almost no relationship, to almost double that relationship. So there's a wide range of slopes here to deal with. And so not only do they start in different places, so people just respond naturally faster and slower, right? They also are responding at different rates. The relationship between these two variables is very, it's variable as well. So the slopes are changing at different rates. Okay. Now what can I do with that? Well, it's interesting. It's problematic because I don't really want to, I want to show that the response predicts the latency. But in this case, what I'm saying is that it predicts the latency, but it's really variable for each participant. So there's probably some other variable out there that explains this heteroscedasticity. Other thing I can look at here is the correlation between the intercept and the response. And it's pretty high. So that means here, this is the worst thing to explain. Anytime there's a high correlation between the slope and the intercept, that means that they're kind of varying together. Meaning, in this case, as participants, it's negative slope. So as participants start higher for their intercept, their latency slopes are getting lower. So in this case, they're an inverse relationship. So as participants have a longer average response latency, their slopes get lower because it's negative, right? Which in this case, lower means more negative. Which, if you think about this, it makes sense. So if I'm starting slower, right, I can get faster with more relatedness. If it's a positive correlation, what you would say is that as participants' latencies get higher, the slope gets higher. So it's a little difficult to interpret, but anytime there is a super high correlation between the slope and the intercept, that means that there's something going on between where they're starting and their slopes. So is this model better than the other model? And it is, unfortunately. Okay, so we looked at this, and it is better. So what that implies is that I need to include this random slope because participant slopes are varying quite a bit. That makes it a better model, so a lower log likelihood, and if you look at the AIC and BIC values, they are also lower. Now, if I were to run assumptions, so that's kind of where I would stop, and I would have to interpret all of these numbers. But let's say we wanted to run the assumptions from the MLM instead of from the fake long data. I would take my final model, the model I decided was my last model, and I would run that. So essentially all I've done is rerun it and called it screen. I'm going to save my standardized residuals. Now residuals are a little harder to get out of these models because it creates residual scores for every random intercept, random slope, and person in this model. So we have to kind of tell it to only give us the ones we're most interested in, which is the fixed effects here. But you can actually look at standardized residuals for the random effects as well, which is in this case slopes and intercepts. So I've scaled those. Now let's look at this picture. And you'll notice it's not much better. So maybe this model would be better as a nonlinear model. So maybe there's something going on there because it actually, this chair picture from earlier got worse. Right? My normality histogram looks about the same. Okay, so it's a little skewed. But you are going to love this. Yep, not much better at all. So even controlling for the error, the correlated error, the participantness here, it got better from the original picture by a lot. But you can see that heteroscedastic slope here. So see how that creates this fan effect. So I'd have to find a good way to explain why there is this fan effect for my particular study. Now I know the dots are there are dots everywhere, but the concentration of dots is heavily down here with this fan out. That's one reason probably why we got those, that random slopes were important, because the participants' residual scores create this fan. All right, so altogether, that is how we would set up a multi-level model, talking about intercept-only models, random intercept models, fixed effects slopes, and then random slope models, and how you would interpret all of those coefficients.